and welcome to the session. I am Dr. Akshay Kumar from School of Computer and Information Sciences, and I will be discussing with you about the recurrence relations. But the very first thing to discuss is what are recurrence relations and why are they needed? Well, a recurrence relation is a representation where a function is represented in its predecessor terms, right? If a function is defined for the nth term, it is to be represented in the form of n minus 1 or n by 2 or some predecessor term of that particular function. Recurrence are very useful in defining the running time and specifically for recursive algorithms. But what are these recursive algorithms? A recursive algorithm is the one which calls itself through the smaller data size, and the example of recurrence algorithm happens to be divide and conquer techniques such as quicksort, merge sort, right, binary search, etc., where we divide the problem into half, right, then we take one half and once again divide that particular half into half, right. So, too many halves here. Okay. So, we keep on dividing the problem and ultimately reach the solution. All right. So, what are the steps of recurrence relations? Well, a recurrence relation consists of just two steps. One or more initial condition, which are also called base conditions, or recursive definition of the problem, that is the second thing which we have to define. So, two things are going to be there. Once again I am repeating, one or more initial condition or base conditions and recursive definition of the problem. Now, take an example of that recurrence relation, a Fibonacci number, right. Now, if I want to represent Fibonacci number, it is basically, it can be represented as with the help of a recurrence relation as fn equals to 0 or 1. Okay. When this will happen? When fn equals to 0? When the value of n is 0, that is Fibonacci number 0 is 0, and then Fibonacci number 1 equals to the value is 1, and thereafter any Fibonacci number is represented with the help of fn equals to fn minus 1 plus fn minus 2, where n has to be greater than equals to 2. What does it mean? If I want to represent f2, it will be f2 minus 1, that is f1 plus f0. So, f2 is going to be f1 plus f0. f3 is going to be represented as f2 plus f1, like that. And that is what will lead to generation of a sequence of like numbers in Fibonacci series, like the f0 is 0, f1 is 1, but f2 is sum of 0 and 1, the previous two Fibonacci number. So, what 0 plus 1 is 1, right. Next Fibonacci number will be sum of the previous two, that is 1 plus 1, 2. Next Fibonacci number will be sum of 1 and 2, which is 3. Next Fibonacci 3 plus 2, 5, and so on and so forth. So, that is the way this Fibonacci number is going to be represented. Okay. So, this is typically a recurrence relation. The recurrence relation which we have represented is fn equals to 0 if n equals to 0, fn equals to 1 if n equals to 1, and fn equals to fn minus 1 plus fn minus 2 if n is greater than equals to 1. What are the base conditions here? For n equals to 0 and n equals to 1. These are the two base conditions, and the recursive definition is fn equals to fn minus 1 plus fn minus 2. All right. Now, another example of this particular situation may be finding the factorial of a particular number. If you remember, we can represent n factorial as multiplication of n, n minus 1, n minus 2 up to 3, 2 and 1, right. So, up to 1, this multiplication is treated as n factorial, and this is valid for the value of n greater than equals to 1, for all values n greater than equals to 1. So, what is f0? that is Fn when factorial 0. Factorial 0 is always defined as value 1. So, how we are going to represent the recurrence relation for the factorial? Well, Fn equals to 1 if n equals to 0, that is the base condition, right. So, factorial 0 is just 1, okay. Whereas, factorial n for any other number is going to be n into factorial of n minus 1. Look into the definition. When we say n factorial equals to n into n minus 1 into n minus 2. So, I can easily convert it into n factorial equals to n multiplied by n minus 1 factorial, right. So, that is what is the basic definition of the factorial as far as recursive definition is concerned. Once again we repeat, n factorial is n into n minus 1 factorial, and the recurrence function representation for this is going to be that first the base condition Fn equals to 1 if n equals to 0, and Fn equals to n into Fn minus 1 if n is greater than equals to 1. So, that is the way we define any recurrence relation. Well, a factorial function as far as program is concerned or a function is concerned can be written as recursively, okay, where n is non-integer negative integer value. So, for that we can write a factorial function, okay, and it can be written as int factorial, and it takes one parameter which is n, happens to be the integer value. And what we check here, if n equals 0, that is we are comparing n to 0, if n is equals 0, then it returns 1. That was our recurrence relation, Fn equals to 1, right. So, this is what it returns. Otherwise, it is return n into factorial n minus 1. This is the exact term which we have represented as a recurrence. So, the function which we have written in C programming or any other language is a direct replica. Okay? It is a direct replica of the recurrence relation which we have represented. Now, how the time complexity of this particular function may be computed, right. So, this is something which we would like to do in terms of once again using the recurrence relation. So, now the time complexity can be computed. For example, we start with n factorial equals to n into n minus 1 factorial if n is greater than equals to 1, right. So, the how many number of multiplications are needed in this particular case? When we start with the first iteration, right. So, it is we are saying n factorial equals to n into n minus 1 factorial, right. So, if I say Tn represents the number of multiplications which are required. So, what we are saying n minus 1, whatever multiplications are required for n minus 1 plus 1, this multiplication which we have performed, right. So, this is how we are going to represent this particular thing. So, n factorial equals to n multiplied by n minus 1 factorial. The recurrence relation as far as number of multiplications is concerned is, that is which is represented by Tn equals to n minus 1 factorial. Computation of n minus 1 factorial will require T n minus 1 computation. That is what is the simple statement. And this multiplication, the multiplication between n and the value, whatever value we obtain for n minus 1 factorial. So, this is one multiplication, right. And at the time when n equals to 0, no further multiplication is required as 1 is returned, right. So, it is simply 1 you are returning. So, T0 becomes 0. So, the recurrence relation for computing the time complexity for the factorial function, it is going to be represented as Tn equals to 0 if n equals to 0, right, because we do not require any multiplication in this particular case. However, it is Tn minus 1 plus 1 if n is greater than equals to 1. So, this is the way we have represented from the factorial problem, right, which is a recursive problem, we are able to get the factorial function. Okay. So, this is what in simple terms we are able to obtain a value, all right, the recurrence relation of or the time complexity of factorial function. Now, in order to get the complexity in terms of what we say the n, we need to solve this particular recurrence relation, all right. Then we will be able to get the actual value of the time complexity. Okay. So, how do you solve this particular recurrence relation? This particular recurrence relation is a very simple recurrence relation, and it can easily be solved with the help of what we say iterative processing. So, let us look into the example for that. So, what is the example? Tn equals to Tn minus 1 plus 1, right. That was the recurrence relation for n greater than equals to 1, all right. What we can say now, Tn minus 1 is going to be, it is going to be Tn minus 2 plus 1, right, and plus 1 was already there. So, Tn minus 2 plus 1 is in the parenthesis plus 1, you got that particular thing. So, it becomes Tn minus 2 plus 2, all right. So, you open the bracket and you get this Tn minus 2 plus 2. Now, Tn minus 2, once again if we represent using the recurrence relation, okay, now what will it become? Tn minus 3 plus 1, right. So, Tn minus 2 is Tn minus 3 plus 1, right. We are using the recurrence relation recursively or again and again, right. So, we get Tn minus 3 plus 1, automatically it will be solved to Tn minus 3 plus 1. So, Tn ultimately will become equals to Tn minus 1 plus n, which is T0 plus n, and the total number of multiplications which would be required will become n. So, the complexity when we solve the recurrence relation Tn equals to 0 if n equals to 0 and the Tn equals to Tn minus 1 plus 1 if n is greater than equals to 1, when we solve this particular recurrence relation, what we get? The value of Tn equals to n, all right. So, that is the complexity of writing this particular factorial function. So, this is the way, by writing the recurrence relation for a recurrent problem, you can solve or you can get the complexity of a particular number. Now, that makes it very interesting. So, let us do a slightly more complex problem as far as recurrence relation is concerned, and one such problem is Tower of Hanoi. It is stated that this Tower of Hanoi is situated in Hanoi. With this particular tower, there are 3 towers. Okay. Now, there are 3 towers, and in one tower there were 64 discs, okay, and those discs are to be transferred from using one tower to the or second tower to a third tower, okay, and there are defined set of moves and defined set of constraints. So, let us define this particular problem, the Tower of Hanoi. The objective of this problem is to transfer the discs from tower 1 to tower 3 using tower 2, right. And the constraint, now constraints are very important in this particular problem. A larger size disk cannot be put over a smaller size disk, okay, and only one disk can be moved at a time. So, what we see, there are 3 disks, one with green color, another with blue color, and the third one is with the yellow color. So, now the condition, the yellow color disk is the largest, blue color is next, and the top is the green disk, which is the smallest. Now, when we move the disk, what we really need to make sure that the blue disk cannot be kept at the top of green disk, all right. Similarly, yellow disk cannot be kept over the top of green or blue disk. So, this is the basic condition or the constraint as far as Tower of Hanoi is concerned. Now, how can we solve this particular problem? Well, we'll give you a solution, but let's try this particular problem solution with the help of recurrence. All right. So, what we can do, suppose there are n disks are in tower 1. All right. So, what we need to do, transfer top n minus 1 disks from tower 1 to tower 2 using tower 3. So, we need to transfer all the disks from tower 1 to tower 3. All right. Now, what we are doing, we are transferring n minus 1 disks from the top to tower 2 using tower 3. All right. So, this is step 1. Then the nth disk is transferred from tower 1 to tower 3. All right. And then since the remaining disks are in tower 2, so what you are going to do, you will transfer the remaining n minus 1 disks from tower 2 to tower 3 using tower 1. So, this is the recursive solution to this particular problem. All right. Now, what is the recurrence relation to this particular problem? Well, assume that Cn represents the number of moves to transfer n disks from one tower to another, right. So, we are giving it a function name as Cn. Okay. Then the Cn will be defined as, it is going to be, how we are going to define, just in terms of our solution, that is, first we are transferring n minus 1 disks from tower 1 to tower 2 using tower 3, right. So, this is basically Cn equals to number of moves to transfer the top n minus 1 disks from tower 1 to tower 2 using tower 3, right. Then one move to transfer the nth disk from tower 1 to tower 3. Then finally, from tower 2, those n minus disks which we have transferred will transfer from tower 2 to tower 3 using tower 1. All right. However, if we represent them using function, so Cn is going to be represented as, since we are moving n minus 1 disk, towers does not matter, the number of moves required will be based on the number of disks, right. So, Cn is going to be Cn minus 1 plus 1 move plus once again n moves, right. So, Cn minus 1, not n moves, transfer on the moves required to transfer n disks. So, that is Cn minus 1. So, the Cn becomes basically twice of Cn minus 1 plus 1. So, what is the recurrence relation as far as the moving the disks is concerned, or the complexity is concerned? Cn equals to 1 if n equals to 1. This is the terminal or the base condition. When only one disk is to be moved, just one move will be required. All right. Otherwise, you will be requiring twice Cn plus 1 plus Cn minus 1 plus 1 moves are required if n is greater than 1. Now, if I compute the time complexity in terms of number of moves, so let's try to compute it. Once again, let's use the brute force method to solve this particular recurrence equation. So, what is our equation? Cn equals to twice of Cn minus 1 plus 1. All right. So, now Cn minus 1 can be represented as twice Cn minus 2 plus 1, which is in the brackets. Okay. The curly brackets, you can see that, and twice was already there and plus 1 is already there thereafter, after the bracket. So, it is finding its place. So, what we get when we open the bracket, we get 2 square plus Cn minus 2 square Cn minus 2 plus, now because 2 is multiplied with the curly bracket 1. So, we are representing it with the help of 2 to the power 1 plus 1. So, we have taken it out into the second parenthesis along with the 1. All right. This is going to, just for the sake of display, we have taken it out. All right. Otherwise, it's one and the same thing. Okay. Now, Cn minus 2 we can represent with the help of, once again, this recurrence equation, twice Cn minus 3 plus 1. Alright. So this becomes twice Cn minus, once again they are in the curly bracket. When we open this particular bracket, we get 2 to the power 3 into Cn minus 3 plus 2 square plus 2 to the power 1 plus 1 and so on. Alright. So towards the end, what you get, 2 to the power n minus 1 into C1 plus 2 to the power n minus 2. So as you keep on doing this particular thing, you will get termination condition as Cn equals to 2 to the power n minus 1 multiplied by C1 plus the terms that in parenthesis 2 to the power n minus 2 plus 2 to the power n minus 3 plus 2 to the power n minus 4 and so on. So this is actually a GP now, right? So technically speaking, C1 was 1. So we get the whole equation, our terms are now 2 to the power n minus 1 plus 2 to the power n minus 2 plus 2 to the power n minus 3 up to 1, right? So we are going to represent sum of n terms of GP, where A is 1 and R equals to 2, and sum of n terms of GP basically is represented as A multiplied by R to the power n minus 1 divided by R minus 1, right. So when we substitute the value of R into this particular equation, we get 1 into 2 to the power n minus 1 divided by 2 minus 1, which ultimately leads to the value 2 to the power n minus 1. Now that is the final, this is the complexity. This is basically defining the number of moves, total number of moves which are required to move n disks from tower 1 to tower 3. That is what happens. Let's experiment this, whether it works or not. Alright. So what we found out, Cn equals to 2 to the power n minus 1. Okay. So let's try for n equals to 2, n equals to 3. So what we get, 2 to the power 3, which is 8, 8 minus 1, 7. So this particular activity should be completed in 7 moves. Now what is the way? Now we are just doing 3 disks, and let us name them. Green disk is A, blue disk is B, and the top disk, topmost disk, or the largest disk is C, let's say that, right. So the constraint is that B cannot sit onto top of A, C cannot sit onto top of B. So our steps will be, the recursive solution is move disks BA, right, B at the bottom, A at its top, okay, into tower 2, right, using tower 3. Then move C to tower C, and thereafter from tower 2, the BA which we have moved, move from tower 2 to tower 3. Now how these activities will be performed? So our objective is to move A and B, right, in that particular, A on the top, B at the bottom, from 1 to 2. So how we are going to do that? First we will move A to 3, right. Let's move A to 3, then move B to 2, right. So we moved B to 2, so at the bottom now B will come in the bottom of 2. Now we can bring A onto top of it, so B and onto top of it A. So how many moves are required? 3 moves. When we are moving A to 3 tower, then we are moving B to tower 2, and then once again from tower 3 we are bringing A to tower 2. Okay. So now B and onto top of it will be A. So these 2 disks will be there, and in 3 moves we are able to achieve that particular thing. Now we move C to tower 3. So that is another move. Okay. So 3 plus 1, 4 moves have already been done. Now our objective will be to move A and B is at the bottom, from tower 2 to tower 3. So what we will do? We will move A from tower 2 to tower 1. Okay. Then B, which is there at the bottom, now can be moved over C, right. So we will move B onto top of C, alright, and then A from tower 1 will be moved to tower 3. So that is the way we will be able to achieve this particular move. okay, all these things will be moved to tower 3. Okay, so how many moves in total? 7 moves, and we are able to solve this particular problem in just 7 moves. All right, so that is how a recursive solution, right? This was interesting, so we demonstrated the solution, but our main objective in this particular session was to make you understand what are recurrence relations and how they can be used in solving the problems, the recursive problems. So if you are given a recursive problem, right, and its preferred solution is recursive function, okay, in which cases it happens? It happens in the cases when a problem can be represented as in the form of its simpler problem, smaller problem. Same problem can be represented with a smaller in terms of its smaller problem. For example, if I want to sort, all right, if I want to sort using let's say merge sort, so what I'll try to do, I'll try to divide a bigger, suppose I'm having n numbers, I'll divide it into two groups. Or let's take an example of binary search. If I want to search in a particular number on n numbers, I'll try to match with the middle number. I'll try to find the value at the middle. They are all in sorted order, and then we'll decide I should search in the lower half or the upper half. So I have divided the problem into half. So I can now do search in the lower half or the bigger half. So I have divided the problem. That means the problem remains the same. So I am able to represent the bigger problem into smaller problem. Okay, 2 smaller problems, or comparison followed by 1 smaller problem, like that. Okay, so that way we can represent the problem into smaller problem, and then recurrence relations can be used to solve that particular problem. And recurrence relations are to be solved in order to represent or find the ultimate time complexity. Otherwise, you will not be able to compute the time complexity of a particular solution. So this is how you will be able to bring in the solution, and then you should always test the solution. Whatever solution you have obtained, once you test that particular solution, only then you will be able to understand whether the solution is correct or not. With this, we end this particular session. Bye for now.